Hello, everyone. Thank you for joining us today. Our speaker for our next presentation is Marco Ribeiro, who is a senior researcher at Microsoft Research. His work is on facilitating the communication between human and machine learning models, which include interpretability, trust, debugging, feedback, robustness, and testing. He received his PhD from the University of Washington. Please welcome Marco Ribeiro, who will be presenting on Beyond Accuracy, Behavioral Testing, and NLP Models with CheckList. Thank you.
Okay. Thanks. This paper was presented at ACL this year. I'm Marco. I work at Microsoft Research. This is joint work with some folks at University of Washington and University of California, Irvine. So this is the problem that this paper is about. How do I check if my model works, particularly my NLP model? So let's say I'm a data scientist or a researcher or whatever, and I train a model, and I even run it on a bunch of benchmarks, enough that I can write a paper on it. Let's say that I call it Oscar. How do I know if it really works? Should I go ahead and, for example, replace my doctor with Oscar if it does well on some medical benchmark? Or if I work at a company like Microsoft, which I do, should I go ahead and use Oscar in our products? So this is a very real problem that people have. You train a model, you have benchmarks, but you want to know whether it's really going to work. And there's many problems with just measuring accuracy. Models can do really well on benchmarks, accuracy benchmarks, by relying on shortcuts that are specific to those data sets that don't generalize to the real world and so on. So we can't rely on accuracy alone, and hence that's why we have Beyond Accuracy in the title of the paper. We want to know whether stuff really works. And in NLP right now, there's this common practice of writing more papers. So you want to know if Oscar works, you write another paper that analyzes Oscar at length. And I've even written some of these papers myself. They're great. The problem is that it's a lot of work. So if you just want to figure out, does my model work? You don't want to have to go and write a paper. There's got to be something simpler. And in this paper, what we're saying is, let's test NLP models just like we test software. We know how to test software. We have some very good principles in there, unit testing and so on. Let's use similar principles to test NLP models so that we can check whether they work or not. So we're going to be borrowing a lot of insights from software engineering into NLP. So I have a little color scheme there. So this is just a sampling of what we did, but one insight, one principle in software engineering is testing small units. So if you're writing software tests, you don't want to test a whole component at once. You test individual functions at once, and then maybe you test a whole component or a system. But typically you start with small units. In NLP, you can't really do that because you have a model. It's typically a black box, and you have some data. So what we're saying is, instead of the small units here are not going to be functions or examples, they're going to be capabilities, linguistic capabilities that are generic to any task, basically. So things like,
Marco.
Go ahead.
I think your screen might be showing just the PowerPoint slide. It's not showing the actual slides. Yep.
Is it? Oh,
yeah.
Sorry. So I've been talking with no slides. I'll try sharing again.
It might be the a different screen if you have to.
Do you see the slides now?
Yep. Perfect. Sorry about that.
Is stuff moving around?
Yeah.
Okay.
It's perfect. Thank you.
Yeah, thanks. So I'm saying we should be testing linguistic capabilities like vocabulary, part of speech, named entities, negation, things that are general, like whatever NLP system you have, it's got to be able to deal with negation in some capacity. So we're saying test whether negation works for whatever task you're doing. Now, in software engineering, there's this principle of decoupling tests from implementation. If possible, you even want a separate team to be writing the tests so that you don't write tests that are specific to how you implemented the code. In NLP, typically what we do is we get a data set and then we split it into training, validation, and test. And that's not ideal for testing purposes because whatever biases you have in training are going to be there in test as well. So we're saying let's decouple the test from training and let's test behaviors with different test types. So we have different test types that we suggest people use. So we're going to be forming a matrix here. Rows are capabilities to test. Columns are test types or different ways of testing those capabilities. And the first one is based on a unit test. So unit tests, you have known inputs and outputs. We're calling this a minimum functionality test, where for a specific capability, you write examples that are as easy as possible, basically. The minimum functionality such that the model can handle that capability. So here's an example. If we're doing sentiment analysis and we're writing a vocabulary minimum functionality test, what we will do is we have very easy examples like, this is a great flight, I hate this airline, I like this seat, and so on. And maybe collect a bunch of those, like 500 of those, and see, does my model have the minimum functionality in terms of vocabulary? Does it have a reasonable vocabulary for sentiment analysis? For words like great, hate, like, etc. So if we're testing negation, on the other hand, the test would be different. It will be stuff that has negation. So this wasn't good, this wasn't great, and so on. So tests tend to build on one another. But again, we're testing whether the model can handle negation in this case. So that's the minimum functionality test. A second type of test is what we're calling perturbation tests. In software engineering, they're called metamorphic tests. And the idea here is that you apply certain perturbations to unlabeled inputs, and you measure certain properties of the output. So you expect something about the output. So one type of those is an invariance test, where you apply perturbations that should not change the label. So here's an example for named entities. For sentiment analysis, if you change different named entities, sentiment shouldn't change. So if you change Chicago to Dallas, the model should predict the same thing, positive or negative, as it predicted before you made that change. Same with Brazil, Turkey, or John, Luke, and so on. Whatever names you're changing typically should not change anything. So that's an example of an invariance test. Another kind of test in the same line is what's called the directional expectation test. And here, instead of expecting invariance, we're expecting a certain property of the output. So for example, if we're testing vocabulary, one perturbation we can apply is adding very negative sentences to the end of examples. So whatever you had before, add, I hate you, you're lame, and so on. And the expectation here is that sentiment should not become more positive. It can be positive, it can remain negative, it just can't become more positive. If I add, I hate you, the model shouldn't become more positive. So that's a directional expectation test. So CheckList is a process and a tool, and it basically is filling this matrix. You look at this matrix, it tells you what to test, it tells you how to test, and then you write tests for every cell and test your model with them. It's very simple. Now you may be thinking, well, you told me I need to write 500 examples. That doesn't seem simple at all. So we actually provide a lot of tooling for writing tests at scale. So we have templating. For example, if you start with, this is a good movie, there's no reason not to create a template that says, this is a, and then adding a bunch of different words that are being suggested here by a language model. And you can imagine doing the same with movie and this, so that you have a template that says, it's a good movie, it's a good book, it's a great book, it's an awesome book, and so on. And you don't have to rely just on your creativity because you're getting suggestions from Roberta here. So this scales testing quite a bit. You can create a lot of examples very quickly. We also have a bunch of lexicons, for example, different names in different languages, country names, city names, in a bunch of different languages, and different fairness things. So we have a lot of lexicons that people may want to use when they're using these templates. We also have a perturbation library with a bunch of preset perturbations and things that make it easy to create new perturbations. We have visualizations. And the point here is that we have a lot of tooling to help people do it. So it's not just a process that we're proposing, there's also an open source tool. So here's an example of a visualization where you're seeing the whole matrix, and you can click on a specific capability, see different tests, and you can click a test and see different examples. In some, we have pretty visualizations in there. You may be thinking, well, this is too simple. You won't find any bugs, and I often get this response initially. So the answer is to just test some models and see whether this helps us get insight or find bugs or something. So we did this in the paper with a few tasks. First task was sentiment analysis. We tested sentiment analysis on Twitter, and we used commercial models. Google, Microsoft, and Amazon all use Twitter as a use case for their sentiment analysis models, which is actually why we picked Twitter. And we also tested some research models that were not trained on Twitter just to see how they would do. So here's the whole matrix that I was describing. I'm just going to show you a few tests just to give you a taste of the kind of things that you find when you run this. So in terms of vocabulary, we wrote an invariance test for replacing neutral words with other neutral words. So for example, if you have the nightmare continues, it becomes our nightmare continues. So clearly that should not change any prediction. Same if you replace that with when and so on. And we're using BERT to figure out what reasonable replacements are. So here's the failure rate for all of the models. If you look at Google and Amazon in particular, 15 or 16% of predictions are changing when you do this semantically irrelevant changes. So that's a bit concerning. We did the rational expectation test that I mentioned before, where we're adding very negative sentences at the end. A third of predictions by Google became more positive, and 13% of Roberta became more positive when we did that. So that's a concern. Robustness, we added random URLs or type or @ sign. So if you're doing Twitter, random URLs should not be changing sentiment, but they change it quite a bit. Like if you look at Amazon, 25% of predictions in this data set are changing if you add a random URL or @ sign. Even Microsoft is failing 10% of the time. In terms of temporal awareness, we try to test whether the model can figure out stuff like, I used to hate this airline, now I like it. And examples like those, you should imagine a template here. So this should be positive. Failure rate is in the 40s for the commercial models. So it cannot handle even very simple temporal things like this. In terms of negation, we did very simple negation, like negating a negative. This wasn't a lousy customer service, should not be negative, should be positive or neutral. Failure rate is surprisingly high, even for very simple examples like these. So these models often tend to think that if there's negation, it's negative, even if we're negating a negative. So failure rate for Google is 54%, Amazon 13%, 30%, Microsoft 19%, and even BERT is failing quite a bit. Another example of negation is just ending with negation. So I thought this would be awful, but it wasn't. And then failure rate is basically 100%. So very surprising that even commercial models can handle very simple minimum functionality tests like these. We did a bit of SRL, so this is semantic role labeling. So different ways of framing questions. Do I think this is bad? No, and so on. Failure rate is also close to 100%. And we have many more tests in the paper. This is just a sample. Another domain we had was Quora question pair, where the task is to detect duplicate questions. And the idea is that if you have duplicate questions, they should point to the same answer on the Quora website. So here we only tested research models, BERT and Roberta. Both are supposed to be better than humans on this task, according to accuracy benchmarks. So they're supposed to be better than humans at identifying duplicate questions. Here's some tests. We're testing modifiers. Is person a teacher? Is the person an accredited teacher? And you can imagine other modifiers. Is this person a professor? Is this person a religious professor? And so on. Failure rate is 78%. Those are clearly not duplicate questions, so 78%. In terms of NER, that's named entity recognition, we have a direction expectation test where we're taking pairs that have the same entity and changing the entity. So if you have two questions about Donald Trump and you replace Donald Trump with John Green in one of the questions, they're not going to be duplicates anymore. And failure rate is still a third for BERT and Roberta, roughly. Another test was to keep the entities and just fill in with BERT. So if we have, will it be difficult to get a US visa if Donald Trump gets elected? Becomes, will the US accept Donald Trump? They're clearly not duplicates, they just have the same entity. Same with the second question on MIT. And failure rate here is, again, 30%. And obviously, no human would think that these are the same question. So these models are failing in ways that humans would not. In terms of temporal awareness, we just tested if the model knows that before is different than after with questions like these. Is it unhealthy to eat before or after 10 p.m.? And we're saying those are not duplicates. Failure rate is 98% for BERT, 34% for Roberta. SRL, we did active and passive swap. So does Anna love Benjamin? Is Benjamin loved by Anna? Any human can see that those are duplicates. It's the same thing. We just swapped agent and object. failure rate is very high, 65 and 98% for both of these models. Another SRL is when we change the semantics. So does Anna love Benjamin is different than is Anna loved by Benjamin, because we change who the subject is, and here failure rate is 100%. So these are very easy for humans. This should be very easy for models that are better than humans, but they're not. Finally, we tested squad, machine comprehension benchmark. Again, BERT is supposed to be better than humans at this. And we did very simple tests like taxonomy tests. There's a large pink bed as the context, and then we ask, what size is the bed? Any human would say large, but BERT thinks it's pink. And for examples like these, it fails 82% of the time. It can't handle antonyms at all. Like if you change optimistic with pessimistic, it can't figure it out, 100% failure rate. In terms of temporal awareness, before is different than after. Like person one became a farmer because before person two, who became a farmer first, last, who became a farmer before, and so on. It fails 83% of the time. Negation completely fails. If you have negation in the context, like Aaron is not a writer, Rebecca is, then you ask, who is a writer? It thinks it's Aaron 2/3 of the time. And if the negation is in the question, like who is not an actor, if you have a context where you have two people, it fails 100% of the time. So BERT can't pass the most basic minimum functionality tests in this case, even though it can answer quite a few of Wikipedia's questions. We had a little test on fairness where we have this template, man is not a doctor, woman is, and then woman is not a doctor, man is, and then we ask who's a doctor, so replace men and women with male and female names. And BERT tends to make very selective mistakes, so it thinks that it incorrectly thinks that the man is a doctor 93% of the time, but it does not make the mistake when the woman is a doctor. And it flips completely if you make it secretary rather than doctor, so that's a bit concerning. In terms of co-reference, we did the simplest co-reference you can think of. Melissa and Antonio are friends. He's a journalist, she's an advisor, and then you ask, who is a journalist? You just have to resolve the co-reference that says he refers to Antonio. BERT completely fails it 100% of the time. Same with former and latter and stuff. So quite concerning. Simple agent object questions like Christian punched Nicole. Who was punched? Nicole. BERT thinks it's Christian 60% of the time. So the conclusion here is that BERT is failing very simple tests. It's clearly not superhuman performance. And actually, we use the same process for all these different tasks and many more since the paper was published. And using the same ideas, using the same matrix, you can find very different bugs in different tasks and models. And another point is that these state-of-the-art models, if you just relied on accuracy, you think that they're almost perfect, better than humans and so on, but they still display many bugs. So you can't just rely on accuracy to evaluate them. And many of these bugs were unknown, we think, before this paper. We had not seen any discussion of this kinds of problems with models like BERT and so on. So you may be asking yourself, how hard is it to find these bugs? Is it very difficult or is it easy? So we did a case study at Microsoft where I went to the team that trained the sentiment analysis model I was testing. And then I asked them, hey, how do you guys test your model? How do you do this and so on? How do you evaluate? And they actually had some pretty good procedures for testing. Like they had a variety of different data sets that they collected themselves and public data sets. They had customer complaints in the past that were added as tests. So this model was pretty stress tested and was being used in production by a lot of customers. And we wanted to see, hey, will it be helpful even for these people to use CheckList? If they already have all of these procedures in place, are they going to find anything? So we did a session with them, 5 hours, where they were testing their own model. Rather than me telling them, hey, I found all of these bugs, they were doing it themselves. And they found many bugs. They found the same bugs I found. They found more bugs because they're experts in sentiment analysis and I'm not. They tested new capabilities that they hadn't thought of. Even capabilities like negation, for example, they had a data set specific for negation, but using this process, they came up with tests that uncovered new bugs that they didn't know about that they could proceed to fix. So the conclusion here is that CheckList can help even for models that are battle tested. We then did a user study where we're having people test, but not experts. These are NLP people, researchers, or data scientists, testing a new model. So they're testing BERT on KQP, even though they have no experience with KQP, for a couple of hours. So we have 3 conditions. Unaided, we just tell them, hey, test this model. Here's access to the model. Test your heart's content. What to test, we gave them a list of capabilities without giving them any tooling. So we basically told them, hey, test negation, test X, Y, and Z. And tooling, we gave them templates. So the 2 on the right are subsets of checklist. And we measure a few things. How many tests did they come up with? They came up with many more tests of checklists in the same amount of time. How many cases did they have per test? How many test cases? And if you have to do it by hand, you can imagine that people did 5 to 7 test cases. But if you have the tooling, templating and stuff, you come up with many more. And the only reason it's close to 200 is because I limited it to 200 on my end so that it would scale as I was running these models. And then we measured how many bugs they found. So this is self-reported, but we had an independent person go and validate this and got the same results. But how many bugs, how many severe bugs did they find on average? And with checklists, it was about 3 times as many bugs. So they have more tests, more coverage, more bugs, and users with checklists found the same bugs we did and new ones. So you don't need to be an expert. A couple of hours using the process is typically enough for a state-of-the-art model, because these models still are quite buggy. But the point is that these people in a user study found a bunch of bugs that were unknown in the literature, so the process must be really helping them. Now here's some reflections after the paper. I've been working with different teams at Microsoft and trying to implement this, and this is the typical reaction that I get. I tell them about this, I show them either this talk or something similar, and the initial reaction is typically skepticism. People are typically like, yeah, it works for you, what you did, but it's never going to work for our domain or for our data or for our model. And then typically I help them out a little bit. I write a few tests and say, hey, check it out. Like, your model has these bugs. Did you know about this? And then people get surprised, like, oh, this can be useful. And then they adopt it. So this is a typical reaction cycle. And I've since then tested way more state-of-the-art models and found many bugs similar to what we've had here, even in commercial models inside Microsoft. Now, what needs improvement in checklists is that the tool needs to have more guidance. Like, I can't expect users to go read the paper and have it in mind. It's an open source tool. I'm still working actively on it, and people need more building blocks. So people are using this successfully. Like, I've had many success cases of people using checklists inside and outside Microsoft. But in order to make it to remove friction even more, I need to add a little bit more guidance and more building blocks, which I'm actively working on. So in summary, if you take one thing away from this talk, it should be this one. You should test NLP models. Don't just rely on accuracy. If you have a model, either in research or using a product, you should go ahead and test it just like you test software. It's not that much work, and it's significantly better than just using accuracy. Now, we try to borrow insights from software engineering and apply them to NLP. So we're telling people, we give them a whole process. What to test, here's a list of capabilities. How to test, here's the different test types, perturbations, and so on. Here's a bunch of tooling. You can have fill-ins, visualizations, lexicons. And I suggest you try it out. So it really, I think, is very helpful in testing models, and it's a tool that I'm working on actively on the open source thing. And also check out the paper if you're interested. There's way more detail in there. Obviously, I only touched the surface here. But that's all I got. I can take questions if there are any.
Yeah, we got a couple of questions. So Walter asked, you looked at the high failure rate ratio for state-of-the-art NLP models. It makes him believe that to think that the current approach of understanding language is far from prime time or production ready. What are your thoughts on that?
Well, it's far from real understanding, I would say. Like, it's not the case that these models are really solving the task perfectly. It doesn't mean that they're not useful. So if you take sentiment analysis, for example, even though we found a number of bugs, it's still pretty good. Like, sentiment analysis works pretty well in production for most cases, especially after you find these bugs, you can go ahead and fix them. Like, some of them are not that hard to fix, the robustness problems and so on. So sentiment analysis, I think, works pretty well. Machine comprehension, like reading paragraphs with Squad, like Wikipedia paragraphs, I'm very skeptical about at this point, even though models are making a lot of progress on benchmarks. I don't think they're ready for prime time yet, but maybe soon. The point is that testing really helps you figure that out.
And I guess a follow-up question from Edward: were the results surprising at all for you? Did you start this line of research because you had suspicion that the models weren't actually as good as the F1 would lead you to believe? And if so, were there any examples of that?
Right. So I had a lot of my previous research was all on explaining this kind of models, and also I had a few papers on adversary. I had one paper on adversary examples. So I had seen a variety of bugs before. I did suspect that they would have significant problems, but I was very surprised at many of the bugs, especially with models. Like if you think squad, like these examples, like these, like models can do pretty well in Wikipedia paragraphs. I expected them to be able to solve problems like this one. There's a large pink bed, what size is the bed? Or to handle very basic negation. Like I thought that would just work. So it was surprising for me that it fails so badly on very simple examples.
And so the other question would be, Ricardo and I guess David would have, I think a similar question is, at which point would you say a company would invest into building their own models versus using what is provided by large companies such as Google or OpenAI?
It really depends, right? Like if you're doing a test that's very specific, you end up having no choice. I think the landscape of things is changing quite a bit with OpenAI releasing their API for GPT-3. So I don't know if I can answer that question yet. If we have such a shifting landscape right now. I do know that there's a significant number of benefits from using what people have already done. Like if you think sentiment analysis, it's hard to do as well as some of these commercial models. Of course, I'm biased. I work at Microsoft. I think Microsoft's model is pretty good, and our tests kind of show that as well. Amazon also did pretty good. So in some domains, the work that they've put in terms of fixing fairness problems and tokenization and so on, it's hard to replicate that if you just get a pre-trained BERT model and run with it. So it really depends. It depends on who you have available. Like if I was at a small company and you said, hey, we need sentiment analysis for this task, I could probably do a better job than using the generic Microsoft one, because I've been working on this for quite a while. So if you have a few PhDs working on it for a while, you can probably do better for specific applications. But it really depends on whether you want to invest that much into each specific model or not. So I think there's a good market for people to be using these company models. But you should test them. Like if you're using one, you should test them ahead of time to figure out which one makes sense.
So Sean has a question about, from a training data perspective, how could you improve the training data knowing that the state-of-the-art models failed most of the tests that you mentioned?
I wouldn't say that they fail most of the tests. I basically showed you guys a bunch of failures, but there's many tests that they do pass. So I'm not saying these models are all worthless. But this is a great question, how to improve it. And it really depends on what you're seeing. Like, I don't think a good solution is to take the templates that you're using for testing and training on them, because that's violating the principle of separating testing from training. So basically what you do there is you probably plug a hole without actually fixing the underlying problem. But sometimes it's kind of obvious what to do. So if you take a test like this one, where the model is not robust to URLs or @signs, well, you should probably be parsing URLs anyway and removing that stuff, unless there are words in the URL. Or if you take an example like this one, squad negation in context and question, if you investigate a little bit, you'll notice that squad does not have a lot of negation. It almost never has negation in questions, and when it has negation in the context, it's typically in a certain form. So this is a clear deficiency in the original data set. So it's clear that if you want your model to work on negation, you should give it some negation examples. So I guess the answer is it really depends on what the test is, but identifying the problem is half the battle.
So Ella asks that what are the first fixes you'd apply when the bugs that you identified in the different test cases? So are there kind of like a blanket fix that you would notice?
No, I don't think I can make a general recommendation that says, oh yeah, you should go and do this. It really depends. Often data set biases play a part. Like these models are very good at learning shortcuts in the data set. So often it's going to be a matter of either removing some data from the data set or adding or going ahead and collecting some new data. Sometimes you can think of data augmentation. Sometimes pre-processing problems play a part. And sometimes what you need is a block list, saying like, if this happens, I won't do anything. Sometimes what you need is to set thresholds where you say, okay, if my confidence is smaller than this much, I'm never going to make a prediction. Otherwise, I'm liable to significant problems. So there's no one size fits all. At least I haven't come up with a good blanket solution to fixing the problems.
And Baltimore asks, what do you think are the next steps for NLP models then?
That's a very difficult question. I don't know. I'm not a prophet, nor the son of a prophet, but I think that they're like this kind of work identifies some good next steps. In terms of testing, I think this is a good start. The problem is how do you go about fixing these models? So there's a few approaches like GPT-3. There's questions as to whether GPT-3 will help a lot of these. I can't comment on that yet, but it does seem like it could be a good direction to have a gigantic model that you figure out how to extract things from. Maybe that would help. I think that there's probably some inductive biases that are missing from these models. If we want to get behaviors that align with these properties that I'm laying out here, and I think we do, we probably need to enforce it a little more or incentivize it a little more with inductive biases rather than just using transformers and hoping that they'll pick up everything. Transformers are great, but we probably need to add some bias in there if we're getting this right.
And so Rajiv asked, we use data augmentation, for example, image rotation for images. In a similar vein, can we use your tool to do data augmentation for the existing training set for the NLP?
Not this tool, I think, because then you'd be training on your tests, which is not a good idea. But I am working on a follow-up paper to this one that's all about data augmentation and stuff like that for NLP. It's a little trickier to do in NLP than in vision. Like in vision, you can come up with these perturbations that apply to any image, basically, like rotation and so on, like or zooming in or out. That they basically always work. With NLP, you have to be a little more careful. But I would not suggest that people take the templates here and apply to and run them on the training set.
So Makto asks, have you explored the effectiveness of transfer learning on correcting off-the-shelf flaws?
Yeah, all of this is transfer learning. All of these, well, not all of them, the commercial models are not, but whenever you see Bert and Roberta here, you should read fine-tune on the data set. So sentiment analysis with fine-tune Bert on SST. TQ core question pair with fine-tune Bert and Roberta on this. So I don't know if this is what is meant by transfer learning, but right now the most standard way of doing transfer learning in NLP is to take a pre-trained language model and fine-tune it, which is precisely what we did.
And I think we're getting a lot of questions about the paper and the slides. Are you going to share them for the purpose, or?
Oh, they are available on my webpage. I guess I can post a link to it. You guys can see my screen. But, oh. I'll post this link here. Infinite loop. I'll stop sharing my screen so we don't get an infinite loop. So here's my web page. It has a link to the paper, different versions of the slides, and even recordings of a similar
Okay,
talk to this one.
perfect. Well, that should be all the questions we have today. Thank you again for joining us, Marco, and giving us such an insightful and useful presentation. And thank you everyone for joining us.